Here's some more examples of how we can use compound interest to find present and future value of a couple different scenarios. Pop a link up if you haven't seen the video for compound interest. I'll pop that link up here at the top of the screen now where you can go check that out. But we talked about these two formulas. We have this first formula where we compound n times per year. And we have a second formula which is when we compound continuously. So we have two types of problems, present value problems, and these focus on the original amount and ask the question, how much do I need starting out to have some amount in the future? So you have some goal you're going to save for in the future. You need $10,000 in 5 years. How much do you need to put in the bank today to have that money in $10,000 in 5 years? Future value problems focus on the future amount and say if I have some original starting amount, let's say I have $10,000 today and I put it in the bank for 5 years, what will it be worth in the future? So that's the two different problem types we're going to work here. The first question, how much money should be deposited today in an account that earns 8% compounded semi-annually so that it will accumulate to $13,000 in 3 years? So this problem is a present value problem because they focus on the amount today and say how much do I need to have today to have $13,000 in the future. Alright, so that's not that big of a deal, but it does help us know what variable we're going to solve for here. So we're going to use, since it's compounded semi-annually, that lets me know that I use this first formula right here. So let's come down and fill in what we know. So as we substitute, you realize we are looking for P, which is why this is a present value problem. Remember, A is the future value. So we have in the future, we want $13,000. We have an 8% interest rate. We compound semi-annually, which means 2 times per year. And we want it to go for 3 years, so we take N times T, which is 2 times 3. So we're going to solve for P here. So the first step here I want to do is I'm going to solve all of this stuff and find out what number that is that's multiplied by P. So let me get my calculator out. And so this time I'm going to demonstrate a little bit more of a different calculator style and what happens when you calculate this. As I mentioned in the last video, there is a potential for error using the calculator here. And here's where the error comes in, is people raise and then they'll say to the 2 times 3. And your calculator follows the order of operations in this scenario, and it raises 1.08 divided by 2 to the 2, and then it multiplies that result by 3. But keep in mind that the 2 times 3 is itself, even though there's no parentheses there, all of that's in the exponent. So the exponent of this problem down here is a 6. And the calculator, if you type it this way, it thinks it's a 2. So if you want to do this way, either do 2 times 3 in your head and put 6 for the exponent, or use parentheses 2 times 3. Alright, so there's just a little area where sometimes people get tripped up on the calculator. So we get 1.2653. So when we put that in, we have 13,000 equals 1.2653 P. So if we want to solve for P here, we divide both sides by this decimal 1.2653. And so on our calculator, we put in 13,000 divided by 1.2653. And so we get that the result is 10,274.24 cents, and it does want us to round to the nearest cent. Since these are dollar amounts, that's 2 decimals. So we go to the decimal after 4, that's a 3, so it's less than 5. So we throw away the 326. So 10,274.24. Okay, so that's a fairly simple example. Now let's scroll down and look at the next one. In 1628, an explorer convinced a group of indigenous peoples to sell them an island for $24. If the indigenous people had put the $24 into a bank paying 6%, how much would the investment be worth in the year 2004 if the interest were compounded A, quarterly, and B, continuously? So this is going to show the two different ways to calculate using compounded n times per year and compounded continuously. So let's write out the first one for part A. Let's write out the equation for that. So here we're trying to find the future value. So we know the present value, and again, present is what it was originally. It's not always like what the amount is today. Sometimes students have that confusion. It's what was the amount of the dollars at the beginning of the process, and it was $24 at the beginning back in 1628. Now we'll plug this into our calculator, and before we do that, just notice I calculated the number of years by taking 2004 minus 1628, which tells me that was 376 years ago, and that number goes there. So on the final one here, I'm going to show you how to calculate this with just the most basic of calculators, like this one here on the computer. So in the case of this kind of calculator, you need to start with your order of operations. You need to be considerate of order of operations, and the first thing is we have 1 parentheses 1 plus 0.06 divided by 4. So we want to do that step first. Alright, so we're going to do 0.06 divided by 4, and then we add 1 to it. So in the parentheses, that becomes a 1.015. And while we're at it, let's get what this number is on the outside. 4 times 376. So that's 1,504. So using a basic calculator, you do need to come down every so often and maybe rewrite your problem to simplify some of those numbers. And so we have 24, parentheses 1.015, to the 1504. So let's clear our calculator and we'll put 1.015, and we're going to come down and find this XY button, which is pretty common on these calculators, to the 1504. We must do the exponent first, and then we do the multiplication times 24. And so you see we get this very large number that starts with 127,391. So let's come over and find the number that starts with 127,391. And you can continue to follow those numbers out to make sure the rest of them are the same. And in fact, they are. 011083. So that means answer choice B is the correct answer for compounded quarterly. Now let's see, what would the investment be worth if the money were compounded continuously? So we've not used this formula yet. So we have A equals P E to the RT. So the initial amount was $24, E, and the rate is still the same, 0.06, and the years are 376. Now, this is where you'll possibly get into trouble on some of these more basic calculators, and you need to have a scientific calculator at this point because many of them don't have the E button on it. So I'm going to pull out the graphing calculator again, although you don't need a graphing calculator. You can use just a plain scientific calculator. And so here we have it. We'll type 24. And so the letter E is typically where you see the LN button. You see right above it, and there's the second feature. If I do second and then press LN, I get E. And notice how my screen says E to the, and it gives you parentheses already. So we're going to say 0.06 times 376. And we'll close the parentheses. Press enter. And so one note about the calculator here. This graphing calculator gives this thing in scientific notation. So this is 1.5 times 10 to the 11th. And we've talked about that previously. But what that means is you would move the decimal over 5 or 11 places from here. Now, all we're really concerned with is we need a number that starts with 150,624,200, and that's what this answer choice B down here does. So again, if you have 1.5, just to truncate it, E11, that's 1.5 times 10 to the 11th, which means take 1.5 and move the decimal over until you go over 11 times, and you can rewrite that number. But again, we were just looking for a number that started with 150,624, and we found that. So I hope these two examples show you a little bit about how to look at present value, future value, and understand compounding continuously and compounding n times per year.